Okay, so chapter 4, section 4, so 4.4. We need to find out, this is actually really simple, so I'm going to kind of blast through this stuff. The goal today is sort of blast through these new concepts, but give you enough information to be able to do all the work that's on the worksheet. All right? You good?
Yeah.
Okay. Just stick with me, and I'm not going to go. I'm just going to go as deeply as I need to go in order to make it possible for us to complete the worksheet. So we're going to go through this material, and then we'll just pick some problems, some off the worksheet that are. I'm not going to do all of them, but we'll pick a problem like of that type, work that problem, and then we'll move on to another type of problem. All right. So this is on 4.4, page 284, and it basically tells us how we can find the trigonometric functions of any angle. All right. So far we've been looking at angles that are like in the first quadrant. It's how we've been thinking about it. But we can, honestly, I think I've already told you guys this. But let's just write down these definitions. Or I think we've talked about it. I don't know if we've actually written down a formal definition. So let's theta be an angle in standard position. What standard position?
Isn't it just the, what's it called? Just that.
So standard position is where the starting side is right here.
Initial side.
All right, that's the initial side.
Yeah, and then the.
So it can be any angle as long as it starts there.
Yeah.
And goes like.
Based on.
All right, so there we go. So there's theta. Then theta be an angle in standard position. And actually, in standard position, it could go in either direction, right? As long as it starts with this, that initial side being there. So standard position with a point with xy, a point on the terminal side of theta, and r equal to the square root of x squared plus y squared. And this not equal 0. So it's got to have actual length to it. So this is our point xy up here. This is our value r. So just the distance from the point. That's r. All right. So if we say that, then we can list these six trig functions for this guy. Sine of theta equals y over r. Cosine of theta equals x over r. I'm going to go ahead and I'm going to write them a little bit out of order because these are just the inverse. So I think it's good to see it this way. R over y, where y does not equal 0. Secant theta equals r over x, where x does not equal 0. Tangent theta is y over x, where x is not 0. And then cotangent theta is x over y, where y does not equal 0. All right. So we can just plug these in, right? For any, this is, it basically looks like what we saw on our unit circle, except here r is any value, right? Not just 1. So sine of theta still has to do with the y coordinate, cosine of theta has to do with the x-coordinate, just like we have in our other scenario. So all of the other ones, they should look pretty similar. But it just gives us the ability, now it doesn't matter what the value is of theta or what the value is of r, whether they're in quadrant 1, 2, 3, or 4, we don't care. We can just plug that in and work those out. So that's that one. And then the other thing is a reference angle. We need to understand what the term reference angle means. So that's the other definition that I want to give you. And this is actually what I talked about before. So when we talk about the reference angle, if we have an initial side here and terminal side over here, and this is theta, then this angle here is our reference angle. And how do they list that? They list that as theta prime. So it's basically, the reference angle is simply the angle as our initial angle relates to the x-axis, right? So if it was here in quadrant 1, then our reference angle would just be what theta is, right? But if we've got a value here in quadrant 2, then it's going to be this angle here. Obviously if it went down here, it would be this angle here, or if we went down here, it would be this angle here. So it's just the angle as it relates to the x-axis, okay? That's what we'll refer to as a reference angle. So what that means, and this is, like I said, this is how I tend to think about the different functions, and this is what, like I said, I'm pretty sure I mentioned this last week, but you can evaluate trig functions for any angle by doing the following. Number one, determine function value of the associated reference angle. So if I'm interested in finding the sine of this angle theta, then the sine of this angle theta is going to be the sine of this reference angle here. But we've got to put the appropriate sign on our answer. Determine sine let's determine sine based on quadrant. And so, what do we mean by that?
You need to find whether the x or the y is negative. So like if the point's like 1, 1, if it's in the first quadrant, it's just going to be 1, 1. But if it's in the second quadrant, it's going to be negative 1, 1. So you're just finding what sign the point is.
So how does that relate to our trig functions? When we think about cosine, we think about what coordinate? The x coordinate, right? And so what that tells us is that if I'm looking at a coordinate plane,
X is going to be negative in quadrant 2.
so cosine is plus, cosine is negative, cosine is negative, cosine is positive, right? Sine is positive here, sine is negative in both of these, right? This is quadrant 1, 2, 3, 4. And then finally tangent for these guys. What's the sign going to be in this quadrant? Quadrant 1?
Positive.
Plus, here it's going to be negative, here it's going to be
Negative.
no, because sine is right. It's going to be positive because it's sine over cosine, right? And then negative here. And then of course, obviously, all of the since cosec, since secant is the inverse of cosine, then it's going to have the same sign that cosine does. Cosecant is the inverse of sine, it'll have the same sign as sine. And then cotangent will have the same sign as tangent. All right? So, didn't I mention this briefly last week? I thought I talked about this idea last
It
week.
might have been the week before.
Huh?
It might have been the week before.
Oh, maybe so. Yeah, maybe so.
I know something about like
All right. So we're gonna. I'm not gonna dig into any examples of any of this stuff yet. I'm just dumping all the information out on you, and then we're gonna work through the worksheet. Okay? But I do want to stop and say, are there any questions? Did I lose anybody anywhere? Is anybody like, I've got so many questions, but I don't even know what question to ask? That's how it all started. It'll make sense. It makes more sense as we start working problems. Maybe we can work one problem from our worksheet. Let me look real quick. Let's see. So it's going to be. So it's. So problems 58 through 61 sort of correspond to this idea.
61?
58 through 61, so
Okay.
we could do any of those. But really, actually, instead of doing that, let's do 69. Because 69 is kind of more in line, I think, with what I'm saying here. So 69, you guys see that one?
Mm-hmm.
So for that particular one, it's like this with 3 pi. Right, that angle is 3 pi over 4. And I tell you with this one here, don't use a calculator, right? Give me the exact value of all of the trig function that I'm asking for. So I'm asking you for cosine theta, where this is theta, right? So the what you're going to think about with this one is your reference angle. What's your reference angle here?
45 degrees.
45 degrees, right? Or pi over 4. So pi over, you can think of it as pi over 4 or 45 degrees. And so once we realize that that's 45 degrees, then we know that we can use one of our special triangles, right? A 45, 45, 90 triangle, which looks like this. 45, 45, that's a right angle, so it's 1, 1, square root of 2, right? So if I'm taking the cosine of 45, cosine is what?
Adjacent over hypotenuse.
It's adjacent over hypotenuse. So that equals, and I can look at either angle. It's going to be the same either way. Adjacent side is 1 over the hypotenuse is square root of 2. So it's going to be square root of 2 over 2, right? Never leave your radicals on the bottom. Did I lose anybody when I went from here to here? You guys remember how we did that? Let's multiply top and bottom by square root of 2. So that's the cosine of 45 degrees, but we're not finding the cosine of 45 degrees, we're finding the cosine of 3 pi over 4. So that means we have to determine the sine based on the quadrant that it's in. Now cosine corresponds to which coordinate x, and so x over here is negative, so cosine is also going to be negative. So our answer for cosine of 3 pi over 4 is negative square root of 2 over 2. So use your reference angle. Your reference angle will, for these types of problems, will give you something that you can easily calculate. And then you just determine the sine based on the quadrant that it's in. Everybody good? Any questions about that?
Wait, so why is it negative?
Because we're finding the cosine,
Yeah.
and cosine corresponds to the x coordinate,
Yeah.
right? And so because it's in quadrant 2, the x's are negative in quadrant 2.
Okay. So 3 pi over 4 is in quadrant 2?
It is, yeah.
Okay.
Right?
So
It goes all the way to
where
there.
it ends, like the line where it ends, not.
Yeah, this line here, the terminal side, right? Where the terminal side is, yes.
Would this get messed up if we used it like in the unit circle? Like if I just looked at the angle and knew like the x coordinate was negative square root of 2 over 2. Would that just work too? Could I just see that? And
Does that work if you've got your unit
Yeah.
circle memorized?
I think so, right?
Yeah, you can do that as well. Yeah. So for these special triangles, that'll definitely work,
Okay.
right? Where you're going to have problems is where you have something like what if I didn't give you, what if I gave you a different angle? So if it wasn't one of your special angles, then you're going to have to use
Use some math.
potentially the Pythagorean theorem to figure out the length of the sides.
Yeah.
But I don't think for these type of problems that there are any problems like that. I think I always use the special.
Yeah,
Angles for
they're
that.
all special ones. You have pi over 4, you have 270, negative 270, pi over 4.
Yeah, so you're good.
So,
It's problems 58 through 61 were the other ones that I was talking about. And let's just do one of those real quick. So let me make a note of which one we just did. So we did 69. And so
will you send out like a sheet of answers so like we know which ones these are, or should we just be able to do it all?
So I'm gonna let me do that right now while I'm thinking about it. I've got the answer key.
Okay.
Send that out to the whole class.
Do you guys want to do this here?
What did I call this? Chapter 3,
4 study guide.
3, 4, study guide. Answers. So it's actually, I think this copy here's got the, like you'll have to look at the end. Study guide, there it is. In other words, it's the study guide is first, and then the study guide with the answer. Or I don't know. Let me see. Actually, I think the answers are just listed out. I think I just gave you guys the geometry one. Close current tab. That is geometry. Yes. Let's go to Precalc. So there's the exam. Where's the study guide? Study guide, there it is. So which one did we just do?
69.
69?
Yeah.
So we said negative square root of 2 over 2. Yeah, this is the right one. Alright, let me try again. Study guide, there we go. Alright, so that way you can check everything. Alright. So do I want to do, I don't think I want to do 58 through 61 yet. We'll talk to the next section and come back to that. Any questions about this? Good? Alright. Jingle bells, jingle bells, jingle all the way. Alright. So let's look at the graphs of sine, cosine, and tangent. That's what the next two sections are about. Does anybody happen to know what the graph is of the sine function? You guys learned that before?
Oh, are we in section 4.5 now?
We're in section 4.5, yeah. Anybody ever seen that before? I can't remember when you might be first exposed to this. Maybe this is your first time. I don't remember. So basically the sine function looks like this. It starts here, goes up to here, goes down through here, goes down here, and back up to there. So this is pi halves, this is pi, this is 3 pi halves, and this is 2 pi. So it looks like this, but it doesn't stop there. It just continues to repeat. But once you draw it there, it just looks the same as it continues to go over and over. Same thing over here, and come down like this, go up like that, and so forth. So that's sine. It starts at x equals 0. And at x equals 0, the y value is 0. This value here is 1. This value here is -1. So it reaches its highest point at pi halves, or how many degrees is that?
90.
90 degrees. Comes down here, hits 0, y equals 0 again at pi. Comes down here, it's at its lowest point, -1, y equals -1 when x equals 3 halves, 3 pi halves, and then at 2 pi it's back to y equals 0. Now if we think about the unit circle, right, what are the points on the unit circle?
0 or 2 pi, then pi halves, then pi, and then 3 pi over 2.
So this point here is 1, 0, right? 0, 1, -1, 0, and 0, -1, right? And this is 0 or 2 pi, this is pi halves, this is pi, and this is 3 pi halves. So sine corresponds to which coordinate?
Y.
Y. So if you think about that, when x is over here at 0, what's my y coordinate? My y coordinate is 0. When x, for the sine, when x is at, for pi halves, the y coordinate is 1. For pi, the y coordinate is 0. And for 3 pi over 2, the y coordinate is -1. So it corresponds to these y values here. Because remember, sine has to do with the y values. We're going to see cosine does the same thing, but with the x values. All right, so let's look at the graph of cosine now. That looks like very similar. The highest point is 1. And the lowest point is -1. And I didn't draw that spacing quite right, but you guys will forgive me for that, because you're just like that, a very forgiving class. So this one starts here, comes down through here, comes down like that, back up like that, and then it just keeps doing that over and over. Like that. And so this is pi halves, this is pi, this is 3 pi halves, and this is 2 pi. Again, this is 1. This is -1, and I'll let you finish writing that down, and we'll talk about that in a moment. So again, to help you remember where it is in each of these locations, if you remember the cosine, this is, I should write down, this is sine. Sine of x, and this is cosine of x, right? Where our x on our coordinate plane, where our x, why am I drawing a blank with that, guys? Our x coordinate, but what is this line called? Our x axis. Our x axis is in radians, right? So we're taking sine of 0 here, radians, sine of pi half, radians, sine of pi, radians there, and some corresponding y values. So we could say f of x equals this, f of x equals this, for this graph, equals. And so again, thinking about it, when the x coordinate is at 0 radians, then the y coordinate is at 1. And when we think about 0 radians for the cosine, our x coordinate is 1. The x coordinate at pi halves is 0. The x coordinate at pi is -1 down here. The x coordinate at 3 pi halves is 0, so we're back up here, and then it repeats itself again at 2 pi. So the unit circle, thinking about cosine corresponding to the x values and sine corresponding to the y values, can kind of help you remember what these graphs are going to do, right? Depending on the angle that you're looking at. Did I lose anybody with that idea? Because it may be a little confusing, because it's like, well, you're talking about x and y, but there's an x, y here, and the x, y's on these graphs aren't exactly the same thing, right? Really on our graphs, these values, the 0, the 2 pi, the pi halves, those are functioning as our x, and then our y values are functioning as what's in the coordinate, depending on whether we're looking at sine or cosine. All right, so like we've done before, what we need to know about these graphs is that these are our parent functions. And so we learned how to transform these parent graphs, right, in previous chapters. These transformations are very similar. We're going to see correlations between some of the things that we've already learned. But does anybody know when you have a wave like this, does anybody know what this distance here is called? The greatest, from the lowest, from the trough to the crest, what that distance there? Anybody know?
Is it the minimum and maximum values again?
What is it? If you took my chemistry class, and I know that there are 2 guys in here that did, I'm very, very upset. I'm hurt, I'm deeply hurt.
Is it the minimum and maximum values, or like the intersection?
Those are the min-max values, but this total distance here, we call the amplitude.
Oh, I didn't know that. You guys know that, right?
Do you guys remember that at all in chemistry? Is it sort of seem familiar? Okay. We looked at it when we were considering light, and so the higher the amplitude, the brighter the light, right? So this is the amplitude. And the amplitude is, if you have for amplitude, if you have y equals a sine of x or y equals a cosine of x, the amplitude for both of those equals the absolute value of a. So for each of our parent functions here, our sine and cosine parent function, what would the amplitude be?
Can you explain that one more time? Sorry, I was writing it down.
I'm just thinking a second here. Did I tell you wrong? I know that's right. Is it? There's just the top and the bottom. All right. Yeah, I told you wrong. I'm sorry. Why did I think that was right? Chemistry. Amplitude's here. Sorry. That's right. You can take it either based on wherever that axis of symmetry is, based on the distance to the crest or the distance to the trough. All right. So either of those could be our amplitude. This would also be our amplitude. Sorry about that. So now let me ask my question again. What is the amplitude of both our sine and cosine parent functions? What's this distance here? 1, right? And that makes sense, because if we think of this as y equals 1 sine of x, isn't that the same thing as that?
Yeah.
So our number in front is 1, so the amplitude is 1 for the parent functions. Make sense? So what that means is that if I were to give you the function y equals 3 sine of x,
The amplitude is 3, and then goes.
the amplitude is now 3, so this thing here, instead of, let me do 2, so I've got a little bit, so I've got more room.
So then instead of going up to its maximizing 1, it goes up to 2.
That's right, everything else is the same as far as the other points. If that's the only thing that we touch, all of the other points would be the same, except it would go all the way up here, and it would come down here, and it would go all the way down here, and it would come up here, and it would go all the way. So it would stretch it out, right? Or it goes to 2 and -2 instead of 1 and -1. All right? Does that make sense to everybody?
Yes.
Yep.
And we had seen that previously with some of our other functions. When you transformed it, when you put that multiplier in the front, it just stretched the function, right, along the x-axis. So very, very similar concepts. Now the period we talked last week about periodic functions and the period of that. So what is the period of this function here? How often is it repeating?
Every 2 pi.
Every 2 pi, right? So it goes. This is all kind of unique y values as it goes across, and then it does the same thing again. The y values will be the same every 2 pi, right? And so when we have the period of a function, we can say, we can calculate the period by, we have y equals a sine of bx, and y equals a cosine of bx. The period is equal to 2 pi over b. So a has to do with the amplitude, that b value has to do with the period. And so if the period changes, whereas the amplitude is stretching this, or it could be shrinking it. How would I shrink it?
Use a fraction like 1.
Use a fraction, right, in the front. Whereas it expands it or shrinks it along the y-axis. If I adjust the period, it's going to expand or shrink it along the x-axis. Okay? So in our case here, like we've already said, the period is 2 pi, which makes sense because I could rewrite this guy as y equals 1 sine 1x, right? So our b value is 1, and 2 pi divided by b is just 2 pi divided by 1 is just 2 pi. But if I said, what about y equals, I'm running out of room here, so let me jump down here to my cosine. Let's say we have y equals cosine of 2x, right? So now my period is 2 pi over 2, which is just pi. And so basically my new function is going to be squished so that it repeats every pi instead of every 2 pi. So my cosine function is going to do this number here. It's going to come down here like this. Right? So it looks like that now, and it's going to repeat like that every pi instead of every 2 pi.
So to transform the functions, whatever number you put in front of the sine or cosine is going to stretch it higher, taller, longer.
Right.
And then whatever number you put in front of the x, if it's a whole number, it's going to shrink it.
It'll
If it's a
shrink it.
fraction, it's going to make it longer.
That's exactly right. Yep.
Okay.
Makes sense? So that's how the period affects things. So the last thing that they tell us is kind of puts the amplitude. This is on page 296. For sine and cosine, if I write it as y equals a sine of bx minus c, or y equals a cosine of bx minus c. And we've already noted that the amplitude is I'll write that down again because I erased it. Amplitude is equals absolute value of A. That's amplitude. This is the period 2 pi over B. The left and right endpoints of one cycle is found, are found by solving bx minus c equals 0 and bx minus c equals 2 pi. So make sure you know these two. If we kind of write our equations finally like this, this is sort of the whole thing written out as far as the possible values that we're gonna mess with, right? We might adjust the amplitude, stretching it along the y-axis. We might adjust the period, stretching it or shrinking it along the x-axis. And then we may add this c value here. And what's the c value actually doing? If you think about what these mean, it's changing the endpoints for one cycle. And so it's basically shifting it along the x and y axis. We did that same thing when we did transformations before, right? So you can figure out what the starting point is by saying bx minus c. So if we did, by solving that equation, if we, what's an example they have here? So they have, in the book, the example they do is y equals 1/2 sine of x minus pi over 3. So our amplitude for this guy is going to be what?
1/2.
Is 1/2. Who said that? Right? So it's going to be half the height of this guy here. We've got a 1 in the front here, so the period's not going to change. The period's still going to be 2 pi, right? But we do see that our starting and ending point are going to change, and we figure that out by saying b, which is 1x minus c, which in this case is pi 3, so pi thirds equals 0. And so when we solve that, we just see that x equals pi thirds. That's our starting point. And the other one that we solve is 1x, bx minus c minus pi thirds equals 2 pi. And so for that, we have x equals 2 pi plus pi thirds, which is going to be, this is the same as 6 pi over 3 plus pi thirds, so that equals 7 pi over 3. This is our ending point. Now it's not the ending point for the actual whole entire function, right? Because it continues to repeat. That's the ending point for one cycle.
So what would that look like on the graph?
So on the graph, what we're talking about then is we're looking at this function here. Let's see if a green one will work. So we're starting at pi over 3, right? Which is smaller than pi halves, right? So it's going to be like, everything's going to be shifted. Wait a minute. No, it's not smaller.
No.
What?
It's smaller.
It is smaller, yeah.
Because pi halves would be 90 degrees, and then pi over 3 would be,
Yeah, it is
pi
smaller.
thirds would be 60 degrees. So basically all the points of the graph just shift over, would just shift depending on where you start and end, right?
Yeah.
Okay.
But I'm trying to think, it's still 2 pi. So,
Yeah.
well, that's still kind of confusing to me because if we shift left, pi thirds, get this right. What am I thinking wrong here, guys? Because if pi thirds is like right here,
Yeah.
right?
Mhm.
Well, 7 pi thirds.
Is right below.
Oh, never mind.
Yeah, you got it.
Yeah, 7 pi thirds is up here, right?
Mm-hmm.
Okay. Yep. So we start here, but remember, our amplitude is 1/2, so we're only going up to this line, all right? So our equation is actually going to look like this, and in each time it's going to cross a little bit right to this side, like that there.
Yeah. So instead of starting at where x and y are both 0, you just start at the pi thirds, right?
What did I do wrong? I do start at pi thirds, yeah, but I did something wrong.
You started at pi thirds and then you went to the point of.
Oh, I'm sorry. This should have gone further. Okay.
Yeah.
Okay. Yeah, there we go. All right. Sorry. One day you guys will have a better Precalc teacher. You're gonna have him after the holidays. He's coming back. It's gonna be a Christmas gift. All right. So this goes up here, and this goes down, and this is gonna go all the way to here, and this goes down here, and then over here it's gonna come back up like that. Right?
Okay. Mm-hmm.
So that's kind of confusing because we got so much stuff on there. Does that make sense?
Yes.
Here's what I want you to see. You can do this, right? And that will always work. And actually, if you have a different period, you're gonna probably need to do that. Not necessarily, but yeah, maybe so. But just if you think about this, remember what happened before when we had a function like y equals x squared, right? And then we did y equals x squared minus 2. What did that do?
It brought it to the
Was it down?
or was it to the right?
Wait, this is inside. This is inside.
Yeah.
If
It's
it's
down.
outside, it goes down.
If it was outside, it was
Yeah,
down.
it was
If it's
down.
inside,
Inside, it goes
so because it's inside the sine function, that's what I meant to do. So x minus 2 squared. Right? X minus 2 squared.
And so that takes it to the right.
So that shifts it to the right too.
Mm-hmm.
This one took it and shifted it to the right pi thirds. You guys see that? It did the same thing. So because it's inside the function, it's doing the same kind of shift that we've already
Yeah,
learned.
because it went from the 0 point and then shifted it over.
Shifted over to pi thirds.
Okay.
The whole thing shifted that way. So this is how I kind of learned to think about it, was to relate it to what we've done before.
Yeah.
This will work, right? But in your mind, I think it's helpful to just realize that it's the same kind of shifting that we've already looked at, right?
Mm-hmm.
Okay, so that's everything that I want to do for sine and cosine. And let's go ahead and work a couple of problems on our sheet here for that. And they are on page so they're the multiple choice ones on page 48, 49, and then also 50 and 51. So let's y equals 4 cosine of theta. So what do we know will definitely be the case for the 4 in the front of cosine of theta?
Will be the amplitude.
That affects our amplitude. What is our amplitude now?
4.
Amplitude equals 4. So that means our graph is going to stretch like this.
And negative 4.
So it's going to go from positive 4 to negative 4. Now if you look at the options that they give us here, there's only one that fits that, right? They actually made this super easy. Would have probably been better to do like a couple that went up before, but then they didn't all cross at the same point. Like one crossed at pi halves and the other one crossed at pi fourth or something like that. But yeah, this one's pretty simple. It's got to be a, right? 49, y equals 2 sine, is it 2 theta?
Yes.
Yep.
All right. So this tells us that the amplitude is 2. The highest and lowest point are going to be 2 and negative 2. And it also affects the period. So the period equals 2 pi over 2, which equals pi. So we're looking for something that goes from 2 to negative 2, but then only, that repeats itself every pi instead of every 2 pi, right?
Yeah, so it's also they give us two options where the amplitude is right, but then the period.
So which one is it? What's the correct answer?
A, because it goes from 0 to pi.
I disagree. Right?
Because it has to repeat
Oh,
It has to
right,
repeat
yeah.
itself every pi.
So then
Yeah,
it would be
it
C.
didn't repeat itself.
Yeah,
It
see,
is
this
C.
is more how I expected the first problem to be, where they give you a couple that are sort of closer.
Yeah.
So yeah, this one, you see how it has to be C? Because
Yeah.
C, the period is pi on C. It repeats itself every pi. From 0 to pi, it looks the same as it does from pi to 2
Yeah,
pi.
it doesn't go a full period in A.
Right. All right?
I'm kind of confused. How is C fine?
Okay, so when you look at the graph, and we know that the sine function, we know that this guy's going to go to 2 and negative 2, right? And so it's going to do like this number here, and do like this, and go like that. So that's one cycle of pi, right? I mean, that's one cycle of sine. But because our period is pi, this value here, instead of being 2 pi like it is on the parent function, is just going to be pi. So one cycle happens from 0 to pi. Because we calculated our period to be pi right here. So only C, you see how you have one full cycle. It starts at 0, goes up, goes down, and then it comes back up to 0 just before it goes up again when it hits pi.
So it has to have a full cycle to hit pi.
That's what the period means, right? So it's going to continue to go like this, but one period, it'll continue to go like that. But one period before it repeats itself is just this section here, right? And we said our period was pi, so it'll repeat itself every pi. So when you go from 0 to pi, it looks that way. When you go from pi to 2 pi, which is another pi, it looks that way again. In this direction, as you go from 0 to negative pi, it's going to look the same. Does that make sense?
Yes.
All right, so what about 50? So 50 has a bunch of them in there, right? What's our equation?
1/2
sine, parentheses 4 theta minus 2 pi over 3.
Minus?
2 pi over 3.
Was it sine? Did you guys say sine?
Yes.
Yeah.
Okay. All right, so our amplitude.
1/2.
So we can immediately see, hey, can we
B and D
rule any out because they go higher than 1/2?
Yes.
Yeah. So our only options for this one are
A
A
and
and
C.
C.
A and C. It's got to be one of those. Our period is 2 pi over 4, so it's going to be pi halves, right? So do both of these go complete a cycle in pi halves? Well,
Wait, what is it?
2 pi 4. How did you get?
How'd you get 2 pi 4?
2 pi 4.
I don't know. I'm just, how did I get 2 pi 4? So the period is 2 pi over b.
Yeah.
2 pi over b is 4,
Oh.
right?
Oh.
Pi halves. I knew what I was doing.
Oh.
Of course. All right, is that right? Does that look right to you guys?
Wait, can you go through the math for me one more time?
Yeah.
Because I understand why the 4 and why it's 2 pi over 4, but then how do you, and then.
So that's 1/2 pi.
Yeah, so then what happens to the 2 pi over 3 that's up top?
That's just the end point. Use that to find the
Say that again. Oh, we haven't done that yet.
Oh, okay.
We're just figuring the period. The period doesn't care about
okay,
c,
okay, got it.
right? Remember, this is our equation bx minus c, so we're just looking at b.
Yeah.
So now we're looking at c, and we know the starting point. So we can think about it like this. Well, let's just see what our starting point is. So if we do bx, our starting point is bx minus c equals 0. So we plug in those values: 4x minus 2 pi over 3 Because remember in our original equation there's a minus in there, so it keeps this, it looks like this, equals 0. So then we say 4x equals 2 pi over 3, and so x equals 2 pi over 12, or it equals pi over 6. That's our starting point.
Okay.
All right? So pi over 6. So which of these look like the starting point is at pi over 6?
A.
Yeah.
Because the other one, when it starts, it's going down like it's got the cosine, I think. Right?
Yeah, because that line in between the pi halves is pi fourth, right? And so pi over 6 is smaller than pi fourths. So it'd have to be to the left side. The starting point would have to be, wait a minute, did you say C?
I said A.
Yeah, A. The starting point would have to be to the left side of pi over 6.
Yeah, I said A.
So A is the only one that works.
Mhm.
Did you guys follow that? Did I lose you anywhere? So we're just kind of ruling out, and I'll just go ahead and tell you all the transformations on the test are going to be multiple choice like this. Okay?
Okay.
Okay.
So I'm not going to have you actually graph it. You just need to be able to recognize how these transform.
And we still get a piece of paper for the test, right? So you shouldn't. Are you still doing that?
Say that again?
We
Oh,
get
like
a
it.
piece
Yeah,
of-
yeah, yeah. You still have
okay.
it. Yeah, you can
Okay.
still use a note card. Yep, absolutely. Did I say front and back on the note card?
No.
You can do front and back on the note card. Just because we got more information, right?
Okay.
It's like two tests combined together. So you guys, I think you guys have that, right?
Yeah.
I don't think I need to do any more, unless somebody needs me to review what I did here. I didn't even bother finding the ending point because I've already narrowed it down to A and C, and so all I had to figure out which one is the correct starting point. And so remember with sine starts here. Cosine starts up here, right?
Yeah.
But sine starts at the x-axis.
Yeah, he started by going down,
Right.
which is a cosine function in this function.
So I'm looking for one that starts at the x-axis where x equals pi 6. All right, starting at that point. And like I said, you got to the math that you have to do there is you have to make sure you understand that pi 6 is less than pi over 4 instead of greater than pi over 4. All right? Has everybody got that in their minds? Because I can walk through that real quick if that's confusing.
So C, it's not C because it's going up on the Y?
So where's the starting point for C? The starting point on C is between pi fourths, x is between pi fourths and between pi halves. Do you see that? You see how it's at the 0 and then going up between pi fourths and pi halves? So looking at it right here, right there, that's the starting point. Can I hold this?
Yeah.
That section there is the first full cycle of pi. I mean, sine.
Why is that the starting point?
Because sine always starts right here. Sine starts at the x-axis and goes up. So that's the first time that we have a first full cycle where it starts at that point and goes up. Does that make sense?
I think so.
So that right there is one cycle of pi, the first full cycle we have of pi. All right, so what I just showed him was for C, if you look at C, you've got pi halves here, right? And for C, we have a starting point. The first full cycle of pi that we have looks something like this, and then down here, and then back up, and like this. Did I draw that right? So does everybody see that when they're looking at C on the graph? This is the first time that we have a full cycle of pi. Starts at 0, goes up, and then comes around and makes its way back up. So it looks like that. So what I'm saying is that because this starting point is between pi fourths and pi halves, it can't be this one. Because pi 6 is somewhere over here. Right?
Mm-hmm.
Because pi 6 is less than pi fourths. Because 1/6 is less than 1/4. Right?
Yeah.
So the only one that fits our scenario is A. Do you see that now, Steve?
Yes.
Okay. All right. So section 4.6 is the exact same thing. Let me see what it is. There's something. I feel like there was something I needed to mention about cosine and sine in that first one. I guess not. Now remember also what you guys have. You have a calculator. Right? So you can check what you think is the case on your calculator and see if what you're thinking about transformation is accurate. I'm just going to very quickly cover this because the concepts are basically the same. But this is the tangent function. And the tangent function looks like this. I just want you guys to see this. I'm not going to test you on the tangent function. I'm just testing you on sine and cosine. Okay? So all I want you to know is that the parent tangent function looks like this. It goes from negative pi halves to pi halves. And you got an asymptote here, and you got an asymptote here. And so it does this right here through the origin. It does this number. And it just repeats that over and over and over. All right, same thing on this side. So that's what the pi function, the tangent function looks like. So just like we saw before with the sine and cosine function, the period will be changed if you put a number in front of the x, right, for tan x. And so there's an example of that on page 305. Example 1, where they say it's tangent of x over 2, which is the same as tangent 1/2 x. Right, so b becomes 1/2, and the period for tangent is what? If you look at the graph that I drew on the board, it's not 2 pi like it is with sine and cosine. How often does it repeat itself?
Pi halves.
Every 2 pi?
It went from negative pi halves to pi halves. So what's pi halves minus negative pi halves? That's pi halves plus pi halves.
So 2 pi halves.
So 2 pi halves, which is pi, right? So period of the tangent function is the period is pi. It's just pi, all right? And so if I say the period is pi, if I say that if I put a half in front of the x, then the period becomes pi over 1/2, which is 2 pi. So like when you see the graph of when you see the graph figure 4.56 on top of page 305, they've stretched it out now, and it runs from negative pi to pi. That's where the asymptotes are instead of negative pi halves and pi halves. So it's a very similar concept. if I had more time, and I don't know, maybe the last day of class, it's in next Monday, the last day of class before the break, we may talk through some more of this 4.6 material just so you are exposed to it, but I'm not going to test you on that. All right, I just want to make sure you know how to transform the sine to the cosine function. Okay? All right, so let's go through let's look at our sheet for the rest of the time that we have left and see if we can just kind of do a sample problem from each section just to make sure that we know how to do all these types of problems. And I want to start with the stuff, because it's the newest material, I want to start with those questions that are at the very end. Which are, so we did a sample question from 68 through 71. Let's do a sample question from 62 through 67. Maybe we'll do 62 or 63, and then we'll do one of the other ones. So I'm asked for the cotangent of theta for a triangle that looks like this. And we have 8, this is theta, this is 15. Cotangent of theta, if tangent is what?
Sine over cosine of theta. Sine of theta over cosine of theta.
That's one identity, but is that the identity that's going to help us for this one?
No.
That's not the easiest way to do it. Okay? SOHCAHTOA. Tangent is
Adjacent over
adjacent over
opposite.
opposite.
Oh no, that's
Opposite
the
over
code.
adjacent.
opposite over adjacent, right? So cotangent, like you said, is adjacent over opposite. It's just the inverse of that, right? And so the adjacent side to theta here is 15. The opposite side is 8. So that's it.
It's just 15 over 8.
It's just 15 over 8, right?
Because it doesn't simplify anymore, right?
That's right. Which problem was that?
62.
62. All right. And then for the other one, for tangent, okay, this one we're going to have to do a little bit of work for. This should have been the one that I did first, but that's okay. That one's really simple.
This is 63.
This is 63, yeah. So we got 16 and we got 8, square root of 5. And they ask us for the tangent. Now, like I said, tangent of theta is opposite over adjacent. We know the opposite, but we don't know the adjacent for this guy. So how can I calculate the adjacent for this one? A squared plus b squared equals c squared, right? I can use the Pythagorean theorem. So a squared plus 8 square root of 5 squared equals 16 squared, right? So if I solve that, I get a squared equals, what is that?
Isn't the hypotenuse square root of 5?
Say it again?
Isn't the hypotenuse c, which is 8 square root of 5?
It is. Oh, I'm sorry, I did it backwards. Thank you.
Yeah.
Yeah. I should have been on that end. A squared plus 16 squared equals 8 square root of 5 squared. Right? So a squared then is going to equal, what is this? This is 64 times 5 plus, no, minus, what's 16 squared? I don't know what that is.
Can we use our calculator?
Somebody punch that in our calculator. Yeah, you can. So you can use your calculator for finding the side. Just don't. But your answer for tangent should be exact.
Yeah, it's 256.
What is it?
256.
That's the final answer?
No, that's for 16 squared.
Oh, okay.
The final
16 squared. Okay. So a squared is 320 minus what'd you say? 256?
Yeah, the final should be 64.
A squared equals 64.
Yeah.
So a equals 8.
Wait, what?
Is that right?
Yeah.
All right. So this side is 8. So now we can figure out that the answer is opposite, which is 16, over adjacent, which is 8. So that equals 2. Yep.
Yep. So we're looking 68. Okay.
So yeah, we'll be in class, so you guys can ask me about that. I don't mind you using your calculator to solve the Pythagorean theorem. I just want you to get exact answers based on the length of the sides once you get the length of the sides. Okay?
Okay.
All right, what about 64? Find the tangent of theta.
If cosecant, cosine equals.
Cosine equals, cosine of theta equals 3 over 5. How am I going to do that?
So cosine is opposite.
Nope.
No, adjacent over hypotenuse. Sorry.
That's right. Cosine theta equals adjacent over hypotenuse. So what you should do is build a triangle
With those.
where we have theta right here. The adjacent side is 3, the top number on the fraction, and the hypotenuse is 5. This is a very common triangle, so
3, 4.
it's the 3, 4, 5 triangle, right? We could use the Pythagorean theorem if we didn't know that and we realized that that other side is 4. But now that I've recognized that, then tangent of theta is just going to be the opposite
4/3, right?
4 over the adjacent. Over 3. And then let's do 66. Cosine of theta, if cosecant of theta equals square root of 5 over 2. Square root of 5 over 2, right? I'm sorry, you guys still doing that one?
So on 66, 5 square root of 5 is the hypotenuse, right?
So yeah, I always like to change this to
Sine.
Sakatoa. So sine of theta equals 2 over square root of 5, right?
Because then opposite over hypotenuse.
That's right. So opposite over hypotenuse. So we've got theta drawn here. The opposite is 2. The hypotenuse is square root of 5.
And then we have to use Pythagorean theorem, right?
That's right. So we have a squared. We can say a squared plus 2 squared equals square root of 5 squared. So a squared plus 4 equals 5. A squared equals 1. A equals 1. And so then to figure out the cosine, it's 1 over square root of 5. Okay, I glanced at the answer a minute ago and I was like, that's not the answer that I see, but this is right. So cosine of theta then equals adjacent over hypotenuse, which is 1 over square root of 5, which equals square root of 5 over 5. All right, so any questions about any of those? All right, let's do one of the last 4 problems, and then we'll back up because I want to make sure we see one of those.
What was the last which problems?
The last one of the last 4, so it's 58 through 61. Oh, wait a minute, that's not the last 4. I want to do on the next to last page, the last 4, 58 through 61. So, let's do 59, for example. So we're asked to find the cosecant of theta and the secant of theta if the tangent of theta equals 6 over 5, and cosine of theta is greater than 0. I don't want to do that one. That one's easier than I want to do. I want to do 61. Okay? So let's find the cosecant of theta and the secant of theta. If the cotangent of theta equals negative 1 over 4, and we know that the secant of theta is less than 0. Okay. All right. So cotangent is the same as the inverse of the tangent. So the tangent of theta equals negative 4 over 1. I'll just think about it like that so we can get the sides to our triangle. And tangent is opposite over adjacent, right?
Yep.
So when I draw my triangle, I put theta here. I say the opposite side is 4 and the adjacent side is 1. Everybody cool with that?
How do you know where to put the theta, or does it matter?
Oh.
Doesn't matter.
What
It's
about,
just make sure that the sides opposite and adjacent to the theta are correct.
what about the negative side? What do you do with
Yeah.
that?
That's going to come into play in a second. First, we can't have negative numbers on the length of our triangle. So let's figure out what our triangle is first, okay? So how do we figure out, we're missing the hypotenuse there,
Yeah, so
right?
we do
So it's just 1 squared plus 4 squared equals c squared.
and that's
So 17 equals c squared. So c equals square root of 17. Right, cool with that?
Yep.
Most of these, I thought really on all these you wouldn't need your calculator. These simple enough for that, so you wouldn't do that. All right, so now they tell us. Why do they tell us that the secant of theta is less than 0? They tell us that so we'll be able to determine what quadrant we're in. All right, so let's think about that for a second. This is quadrant 1, 2, 3, 4. And what we know here is that x is positive, y is positive. X is negative, y is positive. X is negative, y is negative, and x is positive and y is negative, right? So if the secant is the inverse of which other trig function?
cosine.
Cosine.
So it's
And so if cosine is negative, then we know it's going to be where x is negative. So we're either in quadrant 2 or 3.
okay.
Okay? You guys tracking with me so far?
Yeah.
So we're in one of these quadrants. How are we going to figure out exactly what quadrant we're in? Where we look at the sign on cotangent and tangent. The only quadrant between 2 and 3 where we're going to have a negative value for that is if the sign of one is negative and the sign of the other is positive, right?
It'll remain quadrant
So it's got to be in quadrant 2. So that's why they give us that information, so we can figure out which quadrant we're in.
Wait, why are we in quadrant 2 again?
We're in quadrant 2 because you understood we had to be on this side because secant was less than 0.
Yes, got that.
And because tangent is sine over cosine,
Yeah.
right? So sine's got to be, one of them's got to be positive and the other one's got to be negative if our overall value for tangent is negative.
Cosine is equal to x, and then cosine is equal to y, so it's x over y, and then one of them has to be.
One of them has to be negative.
Okay.
Does that make sense?
Yeah,
If we'd
yeah.
been down here, tangent and cotangent would have been positive, right? So we know we're in quadrant 2. So now when we think about 1 over sine of theta, then we know that our sine corresponds to y, so we know it's going to be a positive value, right?
Yeah.
So 1 over sine of theta is, well, let's just do it this way. If cosecant is the inverse of sine, and sine is opposite over hypotenuse, then cosecant is hypotenuse over opposite, right? So this is hypotenuse over opposite.
So that's square root of 17 to over 4.
Square root of 17 over 4. That's right. And is it positive or negative? Cosecant corresponds to sine, which corresponds to our y value, and since we're in quadrant 2, then y is positive.
It's positive, and then secant would be.
negative.
Secant would have to be negative, right?
Yeah.
So secant of theta, if cosine is adjacent over hypotenuse, is hypotenuse over adjacent.
So it's going to be square root of 17 over 1. Which
Right,
is
so it's just square root of 17, but it's negative because we're in quadrant 2. And secant corresponds to the x coordinate. right?
Yeah.
Does that make sense to everybody?
Mhm.
So you've got 3 other ones that you can try at home, and you've got the answers. We're clearly not going to have time to do one from every section like I was hoping we were going to have time to do, but we've done all the new stuff. Let's look at 54 through 57 just real quick. Make sure that you guys understand those. Pick one, 54 or 55. Which one do you guys want to do?
54.
54?
Yeah.
Okay. So with 54, we're going in the negative direction, right? They give us the value in degrees, so I would give your answer in degrees, right? So we know that one rotation around is 360, and then does it make another rotation around? It does not, right? It goes 180, and then it goes another 145 degrees. So our answer is going to be 360 plus 180 plus 145. Right, so whatever all of those total up to be should be our 685. Let's see. Which number was this?
54.
54. 685. Negative 685.
Yeah.
All right,
And then
because it goes in the
opposite
negative direction.
direction.
Yeah. So negative 685. Got to pay attention to the direction as well. The other ones, again, you're doing the same thing. You're going 2 pi, right? It goes 2 pi as you trace it out. And then it goes another 2 pi, so we're at 4 pi. And then it goes pi, so it'd be 4 pi plus pi thirds.
Yes.
Yeah.
All right, so that would be 5 pi plus 5 pi plus pi thirds, so that would be 15 pi, so 16 pi thirds. Think? Yeah. What about finding the reference angle?
You just
Just the distance from which axis?
the x-axis.
Distance from the x-axis. So looking at the first one, the distance from the x-axis is going to be, it's negative 7 pi over 3. So in order to figure out that last angle there, we're going to have to add a 2 pi back to that. You guys see that? So negative 7 pi over 3 plus 2 pi, I'm just going to go ahead and write that as 6 pi over 3 equals negative pi thirds. You guys agree with that?
Yes.
All right. So negative pi thirds is, that's actually our reference angle, right?
Yeah.
But our reference angle, it should be positive. So pi thirds is our answer because whenever we're doing remember we're using our reference angle to do the trig functions, and you always use the positive values for that. So it would be positive pi thirds. And then that last one there, it's just 360 minus 325,
which is 35.
just 35 degrees. Yep. We're basically out of time, but if you want to just glance over it real quick and say, oh, there's one thing here, can you just work one of these very quickly? I'm happy to do it.
First question. You log it back to the logarithm stuff.
Which one?
3 point. The number 1 and number 2 are one of the ones that are there on the first page.
On the first page?
Yeah, just kind
Number 1? Oh, we're calculating interest?
Yeah.
Okay.
Just like a refresher.
Yeah. So we just had 2 formulas that you have to remember. The 2 formulas. One's for compounded annually,
And
that one's continuously compounded, right? And so like number 1, is that one annually or continuously?
Annually.
It's annually, right? And so this one really, I mean, as long as you've got the formula on your note card, you should be good to go
Okay.
with that, right? It's just, I'm just trying to find those formulas. I think it's on page, I thought they had a nice little box that had it all in it. Where am I missing that, guys? How far back was that?
You actually gave it to us in like 3.2 or something?
Was it the very first one?
Yeah, 3.1 or 3.2.
Yeah. So compounding per year, A equals P times 1 plus R over N times NT. So for that one, he tells us that Amy invests 2110, so that's the principal amount, 2110.
So that's the P.
That's the P. Yep. Fixed annual interest rate of 6%. So 1 plus, we always do the percentage rate divided by 100, right? So it'd be 0.06 for R. N is the number of times that it happens per year. So in this case, it would just be 2. And so N again up here, and the N is for how many years? It's for 19 years. So that would be the equation that we have to punch in our calculator and get an answer for. All right. The other one's a little bit. Is it the other one? No, it's Scott invests, Jamie invests, Jasmine invests, sorry. Yeah, so like number 4, just make sure you understand this. Jasmine invests 49, so this is compounded continuously. The compounded continuously looks like this, A equals P, E, R, T, right? And so for number 4, she invests 49.67. With a fixed annual interest rate, E of 4%, so this is 0.04. And they want to know T. They don't give us T, but they tell us that this value is 9. The balance at the end is 9804.25. So this one's a little different than what we've done in the past. Maybe you've done some homework problems like this. But the way we would have to do this one here is we would divide both sides by 49.67. Can someone punch that in a calculator real quick for me? 9804.25 divided by 49.67. So just this is all I'm looking for. Close enough would be fine.
Well, just stare at it.
1.973.
1.973
Mm-hmm.
equals E 0.04T. I just want to make sure you guys know, how am I going to find T? ln, right? So this will help you with some of the other problems as well. So I can say that ln of 1.973 equals 0.04T. Because the ln will undo the e to the power of this. And so then I divide both sides by 0.04. So my answer is going to be ln of 1.973 divided by 0.04. And that will give me the time, the number of years. Okay? All right. And speaking of time, we're out of it. So you guys have a good day. And as you're going through the worksheet, if you have any issues, if you run into that, let me know. Because we will have a little bit of time before we take the test just to answer any quick questions, but it would be better if you send me your questions ahead of time, and I may have time to put a video together, a quick video or something together walking through. Okay? Thank you.